So in this video, we're going to look at properties of the inverse of a matrix. And we're going to assume we have two invertible matrices. It means that A inverse and B inverse both exist, and they're unique, by the way. And I'm going to assume I have a scalar k that's not zero, and I want to find the inverse of the four following matrices: A inverse, AB, A squared, and Ka. The idea here is that I'd like to express the inverse of each of those matrices in terms of A inverse and B inverse. Now there are two ways to approach this. So let's start with A. So solution one, okay, would be, which is algebraic. It's the idea is that if I want to find an inverse, I want to find a matrix such that when I multiply that matrix by A inverse, I get back matrix I. I also need that matrix to be such that if I multiply on the right hand side, I also get back I. So we'll see that in a theorem that's coming up, that only one of these needs to be verified for both of them to be verified. So I just need to verify one of them. One of these needs to be verified. Okay, so we'll see a theorem that shows this later on. Not in this video, but later on in the course. So can you come up with a matrix that satisfies, let's say, the first equation? Can we satisfy this? It's not too hard to see that. Actually, the matrix that I need is A, right? So A times A inverse is equal to I. Okay. So since this is true, then it means that the inverse of A inverse is the matrix A. So I can write this as the inverse of the matrix A inverse is the matrix A. Right? Remember that this equation that I have here, I can read it in two ways. I could say A inverse is the inverse of A, but at the same time, A is the inverse of A inverse. Okay? It's just like saying that, let's say I have 2 times 2 to the minus 1, that's equal to 1. Well, I could say that 2 to the minus 1 is the inverse of 2. Or I could also say that 2 is the inverse of 2 inverse. Okay, so therefore I could write that the inverse of the inverse of 2 is 2 itself. So that's essentially the same thing here. Now, there's a nice way to approach these problems using linear transformations. Okay, solution 2. So let's assume A is the standard matrix of a linear transformation, right? So I'll write this linear transformation with A as a subscript. So that just means that A is the standard matrix of the linear transformation T. So if I apply that linear transformation to X, I'm going to get back AX, right? So the inverse transformation that takes me back to X is T A inverse. So in other words, if I apply A inverse to AX, I'm going to get back X again. Okay, so this just says A inverse times AX equals X again. Okay, so I can read again this diagram in two ways. I could read it this way. So I could, you see, I could apply this transformation first. Okay, that's the transformation with standard matrix A inverse. And to go back to where I was initially, I have to apply the linear transformation with standard matrix A. So that means that A is the inverse of A inverse. Okay, so that's one way of seeing it. So this will prove to be a bit clearer with our next example. So I want to find the inverse of AB. Okay. So let's look what's the linear transformation with standard matrix AB. Well, it's I can write it here. TAB. Okay, it takes X and the output is BX. So the first thing that acts on X is BX. So one way to look at this transformation is that it's a composition of two transformations. First you do the transformation with standard matrix B. This way you get BX. And then you apply the linear transformation with standard matrix A and you get ABX. So we're going, our goal is to go backwards now. So how do we go backwards? Well, to go backwards, we've got to do the linear transformation with standard matrix A inverse, and then we've got to do the linear transformation with standard matrix B inverse. So let's read this. So if I have a vector X here, what am I going to get here? A inverse X. And if I apply the linear transformation with standard matrix B inverse, I'm going to get B inverse, A inverse, X. So the inverse transformation to the transformation with standard matrix AB is the linear transformation with standard matrix B inverse, A inverse. So what does that mean? It means that the inverse of A times B is B inverse, A inverse. We can verify this algebraically, but what I'm showing you on the diagram is that we get this formula just by thinking about our matrices in terms of the fact that they represent, that they're associated to linear transformations. So let's just verify this algebraically. So what I just wrote down over there, okay, let's verify this. So this would be our solution 2, which is algebraic. I've got a matrix AB, and I want to multiply it by something in order to get I. Well, what do I need to multiply it by? Okay. One thing that's not true is that if I do this, I will not get back I. Why is that? It's because these two here, they don't cancel out, okay? And one thing I cannot do is switch. Okay, so this, well, so first thing, this is not I here, so I cannot just cross those out. But you're going to tell me, oh, I want to match A with A inverse. And here's the one thing you can't do. You cannot just cross out these two, okay? You can do that with numbers, but not with matrices. The reason why you can't do that is that the only thing that would allow you to do this is that is when you want to use the identity A inverse A equals I, but I don't have A inverse next to A. I don't have that at all. So I cannot use this right now. Okay, so let me just rewrite them. If I'd like to have A next to A inverse, I would have to switch the order of the multiplication, and I can't do that. You can't do that because matrix multiplication doesn't commute. So this is not the inverse. Okay, at least it's not going to give you I. If you multiply it by AB, it's going to give you some other matrix, possibly not I. So that's not the matrix we're looking for. The matrix we're looking for, well, it has everything I have to cancel. So you see next to my A, I need to put A inverse. Okay, so that now this gives me back I. And to get back, and if this is I times B is going to give me B. And to get rid of B, I'll need to multiply by B inverse. And this is going to give me back I. So that means I need a B there, okay? A B inverse here, sorry. So we see that the matrix I'm looking for, okay, that matrix here that I was looking for, that's B inverse, A inverse. And then it's true that it gives you back I. So maybe if I write solution 2, better way, I would write the following thing. I would write since AB sorry. Let me go back. Since B inverse A inverse times AB is equal to B inverse A inverse A B. I can regroup things like this. This is I. So this is B inverse I B. And this is B inverse B, because I times B is just B, and B inverse B is I. Okay, then B inverse A inverse is the inverse of AB. So in other words, the sentence I just wrote means that AB inverse is B inverse A inverse. So the order of the multiplication is kind of switched when you distribute your exponent. Okay, so this is a major difference with numbers, right? If I have 2 times 3 to the minus 1, I can definitely write 2 to the minus 1 times 3 to the minus 1. But if I replace 2 and 3 with matrices, it's not the same. It's not true. So what would be true is if I switch the order of the multiplication. Then if you replace 2 and 3 by matrices, then it works. But this cannot be generalized to the world of matrices. So that's the identity that applies, and it's very important. And that's due to the fact that matrix multiplication does not commute.